Hi, everybody. I wanted to take a break from chemistry for just a minute and do a short review on um, natural exponents and natural logs, because those are going to come up a lot in the next section. So I thought we'd take just a minute or two, and, well, knowing me, I'm kind of long-winded, so a minute or two will turn into maybe 5 or 10, but hopefully a fairly short time reviewing natural exponents. All right, so let's take a look. Okay, so what are natural exponents? Natural exponents are just exponents, basically, but they are those that have the form y equals e to the x. And this e is a new number. I'm sure that I saw e in high school. It must have been part of their curriculum. But to be honest, I don't remember it from high school. First time I remember seeing it was in college. And so maybe some of you have forgotten it as well. Anyway, this e is technically called Euler's number, and Euler was a mathematician. But most people just call it e. So they would read that equation as y equals e to the x. And where these come up, these functions of this form come up a lot in things like exponential growth, exponential decay, natural growth of populations, things like that. Also in compound interest, things like that with banking. So it's a really common type of function, and so we need to be comfortable dealing with this little e guy. Okay, so what is e? E, in case you're curious, the definition of e is that it is the limit of the function 1 plus 1 over n to the n as n approaches infinity. All right. So if you want to take a look at a couple numbers and kind of crunch them and kind of play around with it, you can make a little table with n and 1 plus 1 over n to the n. So if n is 1, this is going to be 1 plus 1 to the 1, right? Which is 2 to the 1, which is 2, right? If n is 2, then this will be 1 plus 1/2 squared, which equals 1.5 squared, which you can put that in your calculator, and that gives you 2.25. All right. We can go up a little bit higher, put in 5 here. This is 1 plus 1/5 to the raised to the 5th power, so that's 1.2 raised to the 5th, and that gives you 2.49 repeating. And you can keep doing that if you want. It's kind of fun to play around with. Put in bigger and bigger numbers, put in 10, 100, 1,000, a million, right? And when you get to very, very large numbers, as this n approaches infinity, then the value of e will eventually give you 2.718 and so on and so forth. And this is it's an irrational number, which means that the decimal down here, this decimal, keeps repeating, or excuse me, continues on and on without repeating, right? So it's 2.718, I think there's a 3, and so on and so on and so forth. Very long number, but 2.718 is close enough. And to be honest, I put this in here because I think it's kind of fun. It's nice to play around with things like this, looking at the definition, trying to calculate the value of e. But you don't really need to learn the value of e. You don't need to memorize that number because it's already plugged into your calculator. On your calculator somewhere, you have a key that says e to the x. And if you want to do any calculations, like the equation we had on the previous slide, y equals e to the x, if you want to do any of those calculations, all you need to do is use that e to the x key on your calculator. It might be a second function key, so you might have to look around for it if you're not sure where it is. But I promise you it's there somewhere. Okay, let's take a look at a couple of these and practice a couple. Okay, let's practice a couple of these. Let's take, for example, x equals e to the 4.15, right? We want to know what x is. Well, before we calculate it, we might try to estimate it, right? E is a little bit less than 3, and the exponent is about 4. So 3 to the 1 is 3, 3 squared is 9, 3 to the third is 27, and 3 to the fourth is 81, right? So E is 2.7, that's a little bit less than 3, although the exponent's a little bit bigger than 4. Put all that together, and E to the 4.15 should be around 81, probably, maybe a little bit less. Get your calculator, and like I said, you don't need to memorize Euler's number. It's in your calculator, and you have a key in there somewhere that looks like that. All right. So you find that key and just type in e to the x, and then type in 4.15. My calculator requires me to put those in a parentheses. Yours probably does too. And when you do that and you hit the enter key, you should get 63.4. Okay. Now let's try another one. E to the 9.73. Obviously this one's going to be quite a bit bigger. Put this in your calculator. E to the 9.73, and I got something like 16814.55. Okay. So people ask a lot about significant figures for exponents. There is a specific rule for significant figures for base 10 exponents and base 10 logarithms, which we will talk about probably when we get to the acid base chapter. But for this, I would say two rules. One is for natural exponents, you might just make your answer have the same number of significant figures as the exponent. So we got 9.73, that's 3 sig figs. So we might round our answer to 3 sig figs. That's maybe that's not a perfect rule, but at least it's a reasonable rule, right? Another reasonable thing to do is just always round things to 3 significant figures, unless there's a clear reason to do it otherwise. If the sig fig rules are very clear and it needs to be 2 or 4 or something like that, you should do that. But if you're in a place where the sig fig rules are not really clear, 3 is almost always a good number, right? So we might round this one to 1.68 times 10 to the fourth. Okay. Let's try another one. Let's say e to the negative 9.73. Okay. We'll talk about this negative in just a minute, but you can actually calculate this regardless of the negative, calculate it just like you did for the other ones. Just use your e to the x key, 9.73, and what you'll get is approximately 5.94 times 10 to the minus 5. Okay. Now, a negative exponent, of course, actually means reciprocal. So e to the negative 9.73, what this actually means is 1 over e to the 9.73, right? And so based on what we had before, this would be 1 over, what's that, 16,000? 16,814. And when you put that in your calculator, sure enough, you should get 5.94 times 10 to the minus 5. Okay. There's a couple others that I want to do real quickly. Let me see if I can clear out a little bit of space here. People say I erased the chalkboard too quickly. Looks like that's not going to be a problem here, because this is not erased quickly. All right. A couple important ones. E to the 1, right? If we want to know what e to the 1 is, right, obviously any number to the 1 is just that number. So e to the 1 obviously just equals e, right? But you can check that in your calculator if you want. Type in e to the x and then 1, and you should get 2.718, and then that decimal after that, right? And one other one that's important, e to the 0. Any number raised to the 0 power, you remember, is 1. Okay? All right. Let's go to the next page, and I'll give you a couple for you to calculate really quickly. Just a couple simple ones. Run through those, make sure we're all getting the same results, and then we'll move on. All right. So here's a couple for you to work on your own. Run through these, hit the pause button, calculate these, write your answers down, and then we'll compare our results together. Okay, so on this first one, if you use your calculator, you should have gotten 1339, and if you wanted to round that to 2 sig figs, because there were 2 sig figs in the exponent, you could have called that 1300, or if you wanted to just use the general rule that you should probably use about 3 sig figs for most things, you might have called it 1330. Neither of those would be fine. Right? So next one, e to the minus 11.5. This is 1.01 times 10 to the minus 5. E to the 3 is 20.1. And e to the minus 1, what is e to the minus 1? Right? E to the minus 1 is 1 over e, which is 1 over 2.718, right? So that's going to be a little bit more than a third, and so expect something around 0.3 maybe. But if you just put in your calculator e to the x and then hit minus 1 in the parentheses, you should get 0.367. All right, lovely. Okay, that's it for the natural exponents. Now let's go on and let's look at logarithms. All right, so what is a logarithm? Logarithms are written like this, and they've always got a base, which is written down here. Although sometimes they have an implied base, they don't actually have an explicit base, but logarithm looks like this, and the logarithm is just an inverse function of the exponential function. So a logarithm equation looks like this. Log base a of b equals x just means that there is some value. We take a, raise it to some power x, and get b. Right? And so the question is, if we're solving for x, the question is, what value of x makes this true. Okay. So for example, this base here can be any number. So if we take, for example, a base 3 logarithm, right? Log base 3 of 9 equals x. And what that means is if we take 3, raise it to some power x, we get 9. And what is x? What x value do we need to have in order to make that true? And obviously 3 squared is 9, so therefore x is 2. Okay. All right. Let's look at a couple of special types of logarithms. All right, one kind of logarithm that you'll see a lot, in fact you'll see it so often that they're called common logarithms, are base 10 logarithms. So we could write a base 10 log this way, put the little 10 down here. Log base 10 of 1,000 equals x, and we would interpret that as saying if we take 10 and raise it to some power x, we get 1,000. What's the value of x? Okay. So therefore, obviously in this case, x has to be 3 because 10 cubed is 1,000. Okay. But because these are, you come across them so frequently, they're so common, they're called common logs, and for common logs we often leave off that base 10. So anytime that you see a log function that looks like this, and there's no explicit base down here by the log symbol, you should always assume that that means it's a base 10 log, right? And so you'd read that, well, basically as we just said before, right? It's 10 to the x equals 1,000. So if we had one like this, log of 0.1 equals x, right? Then this would mean there's some number, we take 10 and raise it to that number, and we get 0.1, right? And so in this case, x would be minus 1, because 10 to the minus 1 equals 1 over 10, or 0.10. Okay? All right. Now let's look at natural logs, because this is really what we're going for. This is these are the functions that we're going to be seeing in kinetics as we move forward. All right, so natural logs are logarithm functions with a base e. So we could write them this way: log base e of some number y equals x. And what that means is we take e, raise it to some number x, and the result is y. But just like common logs, the base 10 logs, natural logarithms come up so frequently that we have a special symbol for this. And so instead of writing this as log base e, these are usually, as we said before, we call this the natural log. And so the symbol for the natural log is ln, right? So we can write this as lny equals x. And if you see lny equals x, interpret that as meaning take e, raise it to some value x, and the result will be y. Okay. So let's take a look at one of these. We'll calculate a couple of natural logarithms. Oops. Say x equals natural log of 12, and we want to know what natural log of 12 is. Well, we might, one way we could do this is by the kind of check and guess method, right? You might take, well, first of all, let's back up here, right? Natural log of 12 equals x. Remember that means there's some number x such that e to the x is equal to 12. And we want to know what that value of x is, right? So we might just try a couple of values, right, and see if we can find one that fits, right? E is 2.718, which is a little bit less than 3, right? 3 cubed, let's see, 3 squared is 9, 3 cubed is 27, right? So maybe somewhere between 2 and 3, right? Could be. Let's try 2, for example. If we assume that x is 2, e to the x, this would be e squared. You put that in your calculator, and you get 7.389. Clearly, that's too low, right? So maybe we'll try something a little bigger, 2.5. Put that in the calculator, 12.18. Too high, but a heck of a lot closer, right? Maybe it's 2.49, right? Try that. Still too high. Try 2.48. It's 11.94. Now we're too low. Try maybe 2.485. And that gives us 12.001. It's not exactly 12, but it's pretty close, right? And if we're doing things to 3 sig figs, right, that could be our answer. So this is what this means, how you can kind of think of a log like this conceptually, just trying to figure out what value of x satisfies that equation and makes it true, right? But, of course, we've all got calculators, right? And the calculator has a log function, just like it has the e to the x key. It also has the natural log key, which looks like that, L and N, right? Ln. So if you find your, look at your calculator, find the Ln key, you can just type in Ln, and again, just like the e to the x, my calculator puts this in parentheses, so you just put Ln, put 12 in parentheses, close parentheses, hit enter, and when I did that, I got 2.4849, and so on and so forth, right? So rounding 2.48, okay? All right, so let's look at, that's how we do these. Let's do a couple for practice, and then I'll give you a couple to do on your own, I think. Okay, here are a couple to practice. Really just practicing using your calculator, right? Making sure you understand where the buttons are, right? But also, we want to think about what we're doing here. Think about these a little bit conceptually. So, log of 41.6, right? So that means there's some number x such that e to the x equals 41.6. In order to solve that, use the ln key on your calculator, natural log of 41.6, and you should get 3.73. Okay, let's try this one. X equals ln 0.156, right? So if this number here, right, if this number is less than 1, right, then that means it's got to be a fraction number, right? Anything less than 1's got to be 1 over something, right? So we would expect if it's 1 over something, then that x is going to be a negative number. So type in ln 0.156, and indeed we get negative 1.86. Okay. Now here are a couple I'd like to think about, and think about these before you put them in the calculator. Okay. Okay. All right, you might hit the pause and think about these guys. Try to figure out what the answer is going to be, and then go ahead and put it in your calculator and see what you get. Okay. All right, so this first one, ln of 1, this means e to the x equals 1. And what value do you raise something, what power do you raise something to get 1? Well, any number raised to the 0 power is equal to 1. So therefore, in this case, x is 0. And if you put that in the calculator, you should get 0. Okay. Natural log of e, right? Okay, so this is interesting. What this means is there's some number x that if you take e and raise it to that power, you get e, right? So what's that going to be? Obviously, e to the 1 is e, right? And so if you put natural log and then type in the value of e, you'll get 1 back out. Okay. Now how about this last one, right? Natural log of negative 5.2 means we're looking for the value. If we take e and raise it to some value, we get negative 5.2, right? But since e is a positive number, no matter what power we raise it to, we're always going to get some kind of a positive number, right? If x is positive, the value we get will be greater than 1. If x is negative, we'll get a value that's less than 1, but we can never ever get a value that's less than 0, right? So that means that this is not possible. So no solutions, right? And if you put that into your calculator, type natural log of negative 5.2, you should get an error message. Okay. When you're doing your chemistry problems, anytime you end up with something like this, where you're trying to take the log of a negative number, if that comes up, you've made a mistake somewhere. So go back and check your math and see if you can figure out what you need to do to fix that. All right, let's look at the algebra of log equations. Oops. There are two principles here. One is that the log of a product is equal to the sum of the logs. And the second one is that if you take the log of some number that's raised to a power, this exponent comes out into the front, right? So the log of a raised to the b is equal to b times the log of a. All right. We'll need to use those algebraic rules to solve some of the problems we'll be working with in first order kinetics, which will be the next video that we put up. Let me do one more thing with this. This one, I guess we can do this right here. We're using this second equation here. All right. One of the things that is useful for this is if you have something like an e to the x function, and you want to try to solve for that x. To get that x by itself, what you can do is take the natural log of x, right? And what happens then is the x comes out to the front, and you get x times the natural log of e. And as we saw a little bit ago, natural log of e is just 1. And so this gives you x, right? And this works if you have a single variable up here in this exponent, but it can also work if you have a more complicated function. So for example, if you have something like e to the 2x plus 3, you can take the log of that, and that just gives you, just gives you 2x plus 3. Okay. All right, so let's look at some examples of that on the next slide. All right. So let's say we've got a equation that looks like this: e to the 2x equals 26, and we want to solve this and figure out what the value of x is. We can get the x all by itself by taking the log, and if we take the log of one side, then we have to also take the log of the other side. All right. So as we just saw on the previous slide, if you take the log of e raised to some power, you just get that power because the power comes out and natural log of e is 1. So this will give us 2x equals the log of 26, and if you use your calculator to get the log of 26 is 3.258. So that means x is 3.258 over 2, which is 1.69, it's actually 1.6290, which is about 1.63. Yeah. All right, I'm going to give you another one to try on your own, and then I'll show you my solution. All right, here we go. Try this one. 6 times e to the x plus 1 equals 195. Okay, so hit pause and then use the rules we just worked on to solve this for the value of x. And then when you're done, unpause and I'll show you my solution. And in fact, there are 2 ways to solve this one. So we'll look at both of those solutions. Okay, the first way to do this is just to start by getting the e all by itself. So we can get the e by itself if we divide both sides by 6. So this gives us e to the x plus 1 equals 195 over 6. And that's e to the x plus 1 equals 32.5. And then we'll just take the natural log of both sides. So natural log of e to the x plus 1 equals natural log of 2.5 x plus 1, and take natural log of 32.5, just do that in your calculator. That's 3.48, and then subtract 1 from both sides, and x is 2.48. Now, there's another way to solve this. I don't think I have enough room to do this over here on the right-hand side of the screen, so I'm going to go ahead and erase this. I assume you've got that in your notes, and then I'm going to solve this a different way. All right. The other way to solve it is to use that other relationship we had, where the log of a product is the sum of the logs. So if we just start with this and take the natural log of both sides, right, get natural log of 6e to the x plus 1 equals natural log of 195. And on the left, we use that rule that the log of a product is the sum of the logs. So this is the natural log of 6 plus the natural log of e to the x plus 1 equals natural log of 195. And then we just, these logs, we just use our calculator, right? Natural log of 6 is 1.792. Natural log of e to the x plus 1 is just x plus 1. And the natural log of 195 is 5.273. Then to get the x by itself, we just subtract 2.792, right? Because on this side we've got 1.792 over here. We've got 1. So the whole left-hand side is 2.792 plus x, right? So just subtract 2.792 from both sides, and lo and behold, when we do that, we get 2.48. And that's lovely. That's my favorite thing, doing a problem two different ways and getting the same result. When you do that, then you know you really understand how this works, and you can give yourself a smiley face or a warm fuzzy or whatever seems appropriate. And I think that's about it for these guys. Let's just remind you. All right, let's just remind you of what we talked about. We looked at exponential functions, which are those of the form y equals e to the x. And this e is Euler's number, which is about 2.718. That's an irrational number. If you've got a problem with this form and you have the value for x, you're trying to solve for y, you just use your calculator and use your little e to the x key. We also looked at natural logs. And we said an equation like this, natural log of y equals x, is interpreted as meaning there is some number x such that e to the x equals y, and your job is to figure out what that x is, right? And if you have problems like this, you can just use your actually, well, your calculator might say ln x, or it might just say ln. Mine just says ln, but some of them may say ln x. But anyway, just use your natural log key to solve that. We also mentioned that log, I'm going to write this in a general form, certainly true for natural logs, but it's true for any of the logs, right? The log of a product is equal to the sum of the logs. And if you take the log of some number that's raised to a power, the power comes out front, and you get b times the log of a. And finally, This is really important. We use this a lot. Anytime that the x or some function of x is in that exponent above the e, you can get the x all by itself by taking the natural log of that function, and the natural log and the e sort of cancel each other out because they're inverse functions, and so you just get x. All right. These are the equations that we'll be using as we move into looking at first order kinetics. So take a look at these, practice them. I'm going to see if I can get a short set of practice problems posted to go along with the video. Try these. This should be a pretty simple assignment. Work on those and look forward to first order kinetics equations being posted soon. So keep your eyes open, and we'll check back with you in a little bit.